Hello, in today's video we are continuing our discussion on 5.2, properties of rational exponents and radicals. Go ahead and take a minute, pause the video, and see what you can remember about simplifying exponents. One of our rules for exponents is the quotient rule, where if we are dividing, then that means we are going to subtract our exponents. There's 6 5s on top and 2 5s on the bottom, so that means I can cross out all of the 5s from the bottom or reduce all of those 5s from the bottom, and I'm left with just 1. When I do that, what I'm doing is I'm crossing out or taking away 2 of the 5s from the top. So I'm left with 5 to the 4th power, or just 5 to the 4th. Same thing with number 2, because the 6's have the same base. What I can do is say on the bottom, I am going to reduce all of those negative 6's. Crossing them out, I'm just left with 1 on the bottom. All of the 6's reduce. And on top, I have 8, and I'm going to cross out or take away 5 of them. So then I end up with negative 6 in parentheses to the power of 3. Everything on the bottom went away, so I don't even need to write the fraction. I just have negative 6 to the 3rd power. For number 3, remember that a negative exponent means we flip the entire fraction over. So this would become n over 6, and my exponent is now positive. A negative exponent means we take the reciprocal or we flip everything to the other side. Once I have that as positive, I can go ahead and take the 2 and just apply it to everything inside. So I'm left with n squared over 6 squared. For number 4, the exponent is positive, so I don't need to flip anything over. I just go ahead and I put the 2 on top and on bottom. I end up with negative t to the power of 2, which ends up being just t squared, because a negative times a negative is a positive, over 3 squared. So this would become t squared over 3 squared. Again, negative times negative, or negative to the 2nd power, just becomes positive. Number 5, I can reduce down my x's in the fraction. I have 4 on the bottom, so I'm going to take all of them away from the top, meaning I'm left with x to the 1st power, and I'm multiplying by another x. Well, this x here does also have an exponent of 1. And when we are multiplying, all we do is we add the exponents together. So this becomes x squared. Lastly, I'll simplify inside my fraction first. The bases of z are the same, so I just add those exponents together. And I'm left with z to the power of 10 over z to the 5th. And now from here, I have z's on top and bottom. I have 5 of them on the bottom. I can cross them all out. And on top, I have 10, and I'm going to take away 5, or cross out the 5 from the bottom, which leaves me with just z to the 5th over 1. But since I don't need to write the over 1, I'll just write this as z to the power of 5. We are going to use those same properties, but now we're going to use them with rational exponents, or exponents that are fractions. One thing that we saw on the last slide is that if we have the same base, here the 7's match, then all we need to do is add those exponents together. We're multiplying in between the bases, so we add the exponents. So 1 over 4 plus 1/2. I need a common denominator, so I can go ahead and multiply by 2's to make this 2 over 4, which is then 3 over 4. So when I add those exponents together, I end up with 7 to the power of 1 over 4 plus 1/2, which is 7 to the power of 3 over 4. In B, I cannot simplify, I cannot multiply the 6 with the 4 because the bases are different. The 6 has its own exponent and the 4 has its own exponent. The bases are different and the exponents are different, so there's nothing that we can do to combine these. The only thing that we can do is take the exponent on the outside and apply it to everything on the inside. So I'm going to have 6 to the 1/2 times 4 to the 1/3, and each of those is going to be raised to the 2nd power. So I just took the exponent of 2 and put it on the 6 and on the 4. When we have an exponent raised to the power of another exponent, we multiply. 1/2 times 2 is 1. And 1/3 times 2 is 2/3. So this just becomes 6 times 4 to the power of 2 over 3. And that's as far as we can go. We cannot multiply because in our order of operations, the exponents must come first. So if you did want to simplify, we would have to simplify the exponent first and then multiply. But we don't need to do that. We can go ahead and leave it as exponents. In C, we have a few options. Now my exponents are the same on the 4 and the 3. So one thing that we can do is we can almost think of it as factoring out the exponent of 5. But we can do that process that we did in question B just in reverse. They have the exponent of 5, so I can go ahead and pull that 5 out. If there's multiplication inside, this 5 just belongs on each of those pieces, which is exactly what we started with. So we're just reversing or kind of unwinding that process. And then all of this is being raised to the power of -1 over 5. Working inside my parentheses first, I have 12 to the power of 5, and then to the power of -1/5. Exponent on an exponent means we multiply these two. So I get 12 to the power of 5 times -1 over 5, which is just -1. And a negative exponent tells us that our 12 belongs on the bottom of a fraction. So this would simplify down to 1 over 12. Again, since we have the same exponent, we were able to pull the 5 out. And then we can go ahead and multiply our exponents together. And we can multiply the 4 and the 3 together. That's how we got 12 to the -1. And a negative exponent just means we drop the 12 to the bottom of a fraction. In D, I have the same base. On top is 5 to the first power, and on bottom is 5 to the 1/2. So on top, I have 1 5, and on bottom, I have a power of 1/3. So I can cross out all the 5s from the bottom and subtract that 1/3 from the top. If you're not sure, you can go ahead and do the computation off to the side. Getting a common denominator, this would be 3/3 minus 1/3, which is equal to 2/3. So when we subtract, our new exponent is 5 to the power of 2/3. And we can leave it like that. E looks a lot like C. I do notice that we have that same exponent. So I'm going to go ahead and pull that exponent out. So I have a 1/3. And that 1/3 is going to be on both the 42 and the 6. So if we were to work that back, the 1/3 is on the outside of the parentheses, which means it just applies to everything inside. So the 1/3 would go to the 42, giving us what we started with on top, and the 1/3 would go to the 6, giving us what we started with on the bottom. And then all of that has an exponent of 2 on the outside. I'm going to reduce the 42 and the 6. I'll go ahead and divide that down because it equals 7. So I have 7 to the power of 1/3 to the power of 2. An exponent on an exponent just means we multiply. And when we multiply 1/3 and 2, we get 7 to the power of 2/3. Go ahead and take a minute, pause the video, and try these 4 on your own. Go ahead and take a moment, check your answers, and remember to pause and find and fix any mistakes that you may have made. The one I do want to talk about very quickly is number 3. Number 3 does simplify further if we go through the process that we learned in our last video. That denominator of 2 actually means square root. And then I have 4 to the power of 3. Well, the square root of 4 is 2. And then to the power of 3 would give me 8. So I did simplify that one further. If you stopped at the 4 to the 3/2, that's okay for today. We're going to approach the same concepts, but now using radical notation instead. Remember that radicals are just exponents in disguise. Really, this 12 could be written as 12 to the first And since it's under a radical of 3, I would have a denominator of 3. Same thing with the 18, so times 18 to the first, it's under a radical of 3, so we would have a denominator of 3. Well, if the exponents are the same, I can go ahead and multiply the 12 and the 18 and do the exponent on the entire product. When we multiply 12 and 18, we're going to get 216 to the power of 1/3. Or, remember that that denominator does mean cube root of 216, or 216 to the first, but since it's the first, I don't need to write it. When I break down 216, I get 6 times 6 times 6. This is a group of 3 6s, which means that the cube root of 16 is exactly 6. We don't need to break this down into exponents. What we can do is say these 3's mean that the 12 and the 18 have the same exponent. So instead of going through all of this, let's just go ahead and say, well, they have the same exponent, so let's just multiply the 12 and the 18 together to get the cube root of 216. And then from there, the cube root of 216 is 6. I'm going to do that same thing in B. I can see that they both have the same index of 4. So when I divide, I can put the 80 and the 5 underneath the same radical. I don't need to write it as exponents first. 80 divided by 5, when I do that division, I get 16. So this is the 4th root of 16. When I factor 4 times 4, I'm looking for 4 identical numbers, so I need to keep factoring. And sure enough, all of the factors group up into a group of 4, which means that the 4th root of 16 is just 2. Very similarly, we can do adding and subtracting. We can think of this as x plus 7x, or 1x plus 7 more x's. The x is the same, so all we're essentially doing is just counting how many of them we have. Well, we don't have x, instead we have the 4th root of 10. I have one of them, and now I'm adding 7 more of them. If I have one of that 4th root of 10, and I'm adding 7 more of that same thing, what I have is 8 of those 4th roots of 10. If you try and factor 10, you'll get 5 times 2. We're not able to make any pairs, so this is as simple as it gets. For B, same thing, we are adding. Think of this as 2 times something plus 10 times the same thing. So we end up with 12 multiplied by whatever that thing is. Well, in this case, x is actually 8 to the 1/5 power. We have 2 of them and then 10 more of them, which means we have 12 of those 8 to the 1/5 power. We're just counting how many we have altogether. In C, unfortunately, we have 2 different radicals. 54 and 2 are different numbers. The index is the same, which is nice, but underneath is different. So what I'm going to do is factor the 54 and see if we can simplify it to be similar to the radical that we have next to it. When I factor, I get 2 times 27. I'm looking for a group of 3. 9 times 3, and then 9 is 3 times 3. So sure enough, I have a group of 3. So I get to bring the 3 out of the radical. So on the outside, I have a 3. And then underneath the cube root, I have whatever's left, which is that's lonely 2, minus another cube root of 2. There is an invisible 1 here, so if we have 3 of them and we're taking away 1 of them, we get just 2 of those cube roots of 2. Go ahead and take a minute, pause the video, and try working through these 6 on your own. All right, you can go ahead and check your answers. Remember to pause and find and fix any mistakes that you may have made. Our last one here, looks like I didn't finish, 3 times the cube root of 5. And one more slide. Go ahead and again, take a moment, pause the video, and try these 6 on your own. All right, you can take a moment to check your answers. Remember again, pause the video if you need to go back and correct any mistakes that you may have made. Thanks so much for watching, and I hope you have a great rest of your day.